All right, there are quite a lot of participation, 85. That's good. And there are some questions on the canvas as well, from Catherine, Christina, Kevin, Alexander. Okay, let's do one thing. Let us first go through what we have started last day. Let's finish that discussion and then we'll come back to this question, okay? And if we cannot finish this question, maybe we'll address it either I'll write something onto the discussion or we'll address it in the next class. All right. So what we started with, let me go to the Jamboard. Where is my Jamboard? There. Yes. Okay, so we were drawing some overall system architecture and diagram of a computing system like a processor and memory together, and we have shown that inside the processor we have the controller, register file, etc. I basically like drew them little neatly last night. I believe I saw some of you were watching me, maybe. I don't know. I always see some people are looking at my this Jamboard. But anyway, so basically these are the same picture. Ugly hand-drawn picture, okay, not so Picasso style. Okay, this is not even Picasso style, but anyway, we have just kind of a little bit neatness there. So we will start our discussion based on that point where we ended last day. So I have taken a snapshot of the picture so that I have enough space to actually describe a simple, very simple one-liner program. And this is again a review from CS147 organization class. And basically we will discuss that again here to refresh your memory on how a processor works. And maybe that will answer some of the question from Kevin in the canvas about these cycles and instruction fetch, etc. Let's see. So let's concentrate on our. So we'll try to review what happens with a very simple high-level program. Very simple high-level program, which defines like maybe a little bit of defines a small program like this, like integer a equals 10, integer b equals 20, integer c equals a plus b. So let's, where is my equal here? Let's try to understand what happens with this very simple program. First of all, these high-level variables in the high-level program are basically nothing but they are mapped into the address, one of the address in the memory. Okay? So let's assume A is at memory address 0. This is at memory address 1. This C, actually I should. C at memory address 2. What I mean is this, like this one, this address
is storing the value for the A, this address storing the value for the B, and this address is storing the value for the C. So that means I have in this memory address, I have 10, and then I have memory address B, I have 20, and let's say C is initialized as 0. And now, as you recall, the high-level programs, high-level program like even one statement C equals A plus B, it is not like at the low-level program can be executed directly like that. We have to basically split it up in multiple assembly level instructions, like for example, maybe at a very abstract sense, maybe it is like this: R0 equals memory 0, R1 equals memory 1, and then let's say R3 equals R0 plus R1, and then memory 2 equals R3. R3. So let's try to understand what's going on here. So very first statement is saying that read from the memory location 0 and store it in the register 0. Okay, and then next instruction saying read from memory 1 and store it in register 1. Then the next instruction say is the read from register file of the register 0 and then register 1, add them up, store it back in register 3, and then it is fourth statement is saying that a memory write into the memory location 2 with the value retrieved from register 3. So one simple high-level instruction, C equals A plus B, is basically broken down into 4, right? 4 basic instructions. Okay, and it happens to every high-level instruction you write. They are broken down into like 2 or more different instruction at the assembly level and machine level. So so I hope you guys can write actual assembly code, let's say using our CS147 DV, that made up language we are making up in this class. You can write them. Okay, that's a different problem. Now let us get back to the other story of this. So far, any question from any of you?
Will we be doing any actual assembly program writing, or is it all modeling and simulation?
It's all modeling simulation, but in the project, you will need to write your little assembly program and translate into corresponding machine code. That's where you actually need your CS47 or equivalent ideas, where you basically write a little test code in assembly and then translate that test code into machine code by hand and then throw it in the simulation environment. So that's the expectation. So we won't be doing any real assembly programming in classes. Only for the project testing purpose, you will need to do something. Okay. So now let's assume we all know from the previous classes, right? This instruction, there is corresponding machine code representation, and they all are stored in a part of memory. Let's say they are stored some part here, okay, some part here. So maybe they start from an address 100, and next instruction at address 101, the next as 1002, and next at 1003.
So let's say this part has those machine code content. So memory has both data and the source code
or program to be executed.
So now what happens is that when we power up the whole system, your controller is powered up with a known address. Let's say it's in this case 1000. So this address is called the initial address that a program counter register inside the controller stores the power up address. Okay, this is what we call the power up address. If you look at the CS147 DV instruction set architecture, you will see that instruction set architecture has an assumption of the power up address for the program counter. There is stack pointer and other default register that has to be power up at a specific value. So please pay attention to that. But for today's discussion, let's assume our power up address is 1000, and that's what appears in the controller program counter register when you power up the machine. There are other two registers. One is the instruction register that intermediately stored the instructions incoming from the memory. And there is another like accumulator SEC, but it is like I've just placed it as a purpose of explaining things. There is nothing major role there. In fact, the controller you will be implementing in this class won't have any accumulator register, and everything is done through the register file. But this is just for our, let's say if we need that to understand or clear up our concept. So now this processor, when it starts in a state called instruction fetch. At this point, at this state, processor issues an address coming from the PC, which is 1000 now, right? This PC's address is sent to the address line, to the memory. And then read signal is made 1, logic 1, and write signal is made logic 0. So that means to the memory, it is that someone is requesting to read from an address 1000. And what that address content is a machine code for this instruction. R0 equals mem0. So we don't know what the machine code is. Let's just assume it returns something back. Let's say some instruction machine code it returns back towards the controller. It returns back to the controller, and that being written into the instruction register somewhere. So that's what is done or what happens in the instruction fetch stage. Now, from this step, controller goes into something called instruction decode and register fetch. Okay, let's concentrate on the instruction decode part. What happens? So at this point, controller somewhat decode this instruction and gives a meaning to this machine code, that it knows by decoding the instruction that it need to access the memory and read from that an address, store the value coming from the memory into the register 0. That's what it understands from the decoding step. So what it does after this understanding is done, then it goes to the exe phase, execution phase. This execution phase somewhat involves ALU and compute address, memory address to be read. it compute the memory address needed to execute this instruction, okay, this read from the memory on a specific location. Then it goes to the mem state. In this state, now processor or this controller knows from the decoding of the instruction that it has to read from the memory. So it issues the corresponding address. So in this case, it will be 0. And the read signal, it sends the read signal to the memory. So at that point, memory returns back from reading from the address 0, which is 10, right? So it basically returns back 10 to the controller. Let's say controller places that value in this accumulator. Let's just for discussion. So now controller goes to write back stage. So at that stage, controller knows that from the instruction decode step, it knows whatever data comes from the memory state, I need to write it back in the register 0. So what it will do at that point, it will send our address write as 0 and data as 10. This data is coming from that's intermediate storage to here, okay? And the 0 being generated from the instruction register by decoding and etc. And it will set the read signal to the register as 0, write signal to 1. So as a result, what will happen at that point, register file will write this value 10 onto the register 0. So it will write that value on the register 0. And at that point, another things happen. That is, it updates the program counter with increasing by 1 so that it points to the next instructions. Basically, it updates the program counter at that point, and then processor goes into the instruction fetch again. So that's end of execution of first instruction. Okay. Question so far?
Hey, Professor?
Yes.
How could the program start address, I think that's what you called it, or the startup address, how could that be stored on the processor when the whole point of having like a hard drive is that all the data gets wiped off your processor when you turn the power off?
So it's basically it's an hard-coded power up address, and it is being specified in any handbook of any processor. If you look at the processor manual, it is always hard-coded address that operating system needs to follow.
Okay.
So it is always be at that address.
I have another question.
Yes.
So in the instruction decode phase, so if we were on like an add instruction, then at that stage we would fetch the registers. So we would like get a read from the registers, the two operands, and then that would be the instruction decode phase that would include the register fetching.
Yes, exactly. We'll come to that. Like I think on the third instruction, the 1002 address, we'll see that that instruction decode at that point, controller also made a register fetch if needed at the same point, at the same stage.
Also, can you repeat at what stage does the program counter increment? Is it
it's
right
when it goes from write back to instruction fetch, at that point the program counter get updated.
Okay. All right.
So you can say write back phase, program counter get updated to it's getting ready for the next instruction fetch basically.
Thank you.
Any other question? Okay, now next, so that means now what happened in this instruction fetch state, your program counter is updated to 101 and your controller will happily issue that address to the memory, and we don't know what is that. This is a read operation. And now memory knows at this point that I need to read from address 1001. So it will return the machine code stored corresponding to this instruction, R1 equals in mem1. So it will return that. And let's say that's called maybe, I don't know, ANXXX, something, right? So that's being stored, let's say, in the instruction register from the memory, whatever incoming. And then on the instruction decode phase, it goes into the instruction decode phase, and it now knows, okay, now it need to read from the another memory location and put it back into register 1. So same thing happened that happened at the previous instruction. It computes the memory address involving the ALU somewhat, and then issues that address in the memory state, issues that address. Now it will be 1 and read signal. So it issues that address to the memory. So at that point, when memory gets that instruction, read from the address 1, it will return the value 20. Then controller stored the value 20, let's say in some intermediate register inside the controller. Then it goes to the write back phase. So write back phase, what happens in the write back phase is now controller issues one, because we need to write into the 1, and the value 20, which comes from this, right? 20 came from the memory read and goes into the register. So at that point, it will write 20 into the register 1. And it will update the program counter now, right? It will update the program counter. So program counter now become 1002. And then it goes to the instruction fetch, from write back to instruction fetch. So at that point, controller issues 1002 to the memory with a read signal on. So memory will read from the address 1002, whatever the machine code corresponding to this instruction, and will get back into the controller, and controller will store that into the instruction register. Okay, store that in the instruction register. Now in the instruction decode phase, now processor goes into the instruction decode phase. So there it understands that it has to fetch values from 0 and 1, add them, and store it back into register 3. So what it does, it basically at the same point, register is read. Registers are read at the same point. So at that point, this guy will issue an address of 0 to one of the read address, and another as 1, and read signal to 1, write signal to 0. Okay, and see the other signals, ADDRW and data W, don't care. And if you don't care something, usually you can assume it is a 0 for the hardware, because it won't be reflected anything there. We're not writing. So it doesn't matter what value is set. Main focus on these 4 signal status, right? Address 0 and address 1 and
It is a read. So as a result, at that point, register file will return these two values, 10 and 20, onto these data port, data R1 and data R2. Now, controller will go into the exe phase, where it basically involves ALU for the operation. ALU for the operation. So now it involves perform addition, in this case, using ALU. So what it will do basically, it will send like 10 as one operand, 20 as other operand, and some encoded value to as an operation for which denotes the addition. Some value, maybe it is 2 or 3, depends on the ALU specification, what value denotes what, but it basically sends the operation request as addition. So these 10 goes here, redirected from incoming from the registered file, outgoing to the ALU, and another one is incoming from the register file, that 20 outgoing to the ALU as operand 2, and operation code is generated as addition. So what ALU will do, ALU will add them up and sends 3 back to the result. Okay, back to the result. So maybe let's assume that 30 is being intermediately stored at this SEC register. Okay, but it doesn't need to be. What all the purpose is that we somehow need to now store this 30 value to the R3. However, at this point, we are still in the exe state. So it will still go to the mem state. So since this operation does not involve any memory, so it will basically stay there, do nothing. It will still go into that state, but it will do nothing. And then it will transition from here to write back stage. So at the write back stage point, what will happen to the register signals is this, is basically address W will become 3 issued by controller because it is coming from the instruction. Register 3 has to be written with the result. And the data W will become 30, which is coming from here, right? Which is coming from the accumulator. Or you can imagine it is directly coming from there to here. From the result, from the ALU, and redirected to the data W port from the controller. And read-write signal will become, read becomes 0, write become 1. That means at that point, register file will write 30 at register 3. And at that stage, your program counter will be updated for the next instruction, which is 1003. Now it goes from write back to the instruction fetch. And what happens at that point? Address 1003 coming from the PC program counter, it will just redirect to the memory by the controller. It still read, and memory then it will read from the 1003 at address, the machine code, return it back. It will be stored in the instruction register, and controller will go into the instruction decode phase. Now at this point, for this instruction, controller kind of decode, understand this instruction like this. It has to fetch the register 3 and store it back into the memory at some address 2 for this example. Then what it will do, it basically is at the same stage of instruction decode register fetch, instruction decode and register fetch, it will basically try to read from the register like this. It will set the control to the register to 1, write to 0. Maybe address of R1 is set to 3. It doesn't matter what the others are, because let's say it is set to 0. Okay, so what will happen as a result of the reading from the register file is written on the data R1 port as the value 30, and data R2 port, since the data address R2 was given 0, this will be written as 10, but controller will anyway throw this 10 away because you don't use it. Basically looking for this one, which is coming from the register 3. So it will pick up this guy and it will hold on to that, right? It will hold on to the accumulator, the 30 in the accumulator. Now it goes into the exe stage. And the exe stage, it will compute address to the memory, which will become 2 after this computation. And then it goes into the mem stage, which basically now will issue this thing, right? 2 as an address, value 30. So this 30 is coming from this to that, right? Accumulated to the data. And it will set read to 0, write to 1. So as a result, what will happen, memory at this point will write 30 at address 2. And this 30 at address 2 belongs to the high-level variable C. That's where you get your variable C value get updated in the high-level program, in the high-level programming sense. And then it goes to the write back. There is nothing to write back in this point. So it is nothing happens in the register point of view. It will just update the program counter to the next value. It will increase the program counter to 1004. And we don't know what happens. We don't know what the program, rest of the program looks like. But that's the life cycle of one single simple statement, C equals A plus B. So you see that we actually need to break it down 4 statements, and each instruction, each statement needs 5 cycles to be executed, right? So that means this one simple high-level statement, C equals A plus B, needs actually 20 cycles to get it done. 20 cycles get it done. And I needed like almost what? 35 minutes to explain one simple high-level statement to you guys. But it's, of course, in a computing sense, it's a blazing fast, and we all know that, right? Question?
I have a question. I want to clarify on the like mem2 is equal to R3. That's that statement. So in the instruction decode phase, we need to get, I think, 2 register files, right? We need to get the register file that contains that R3. We need to get that register file, the value for that, and we also need to get like the another register file or 2 in order to calculate the memory address. Because
we don't need it, right? Because this read operation for this register file is always for the 2 registers, because simply has 2 address for the register, address 1 and address register 2, right? But controller is interested only 1. It will still issue some dummy address to here, maybe 0 or something, right? But it will only look for the data of the R3. So is that the question, Kevin, you have?
I remember last semester, I thought that this memory, like the loading and the writing, it's an I type instruction, right? So that means that in order to calculate the memory address,
Yes.
in order to calculate the memory address, you have to add together the contents of RS and the immediate together in order to calculate the memory address. So,
Yes, thank you very much, Kevin. So what you are saying, you are actually going into detail of the basically how that in reality what happens. So let me, yeah, that's a good point. That's a good point. Let me try to explain what you are saying it, right? So for it, so that everyone is in the same page. So basically what Kevin is saying, that this memory operation, right? This is practically these instructions: store word R3, then it's always a base register reference. It is an indirect references that basically involves another register, let's say R5, with some indices, let's say 2. So this is always a format. This is always a format for a store operation like this. Memory 2, address 2 is content of register 3. Now this address, how it is actually encoded in terms of real assembly language, it is with respect to some base register and some indices. So this means look at the content of register 5 and add 2 on top of that. Okay, add 2 on top of that. So that means in reality, if you look at the real piece of assembly language, at the instruction decode phase, you need to read back from R3 and need to read back from R5. Okay, so R5, so that means your in this example, your R2 become like 5, and maybe that has 0 in it, so it will return 0. Okay, it will return 0, and then at the address computing step, what it does, it basically use this 0 to the ALU. So it will send the ALU this thing 0 and another, and then it will send this 2, this immediate field from the instruction which is stored here. So it will send these 2 over here and do an addition, then result will become 2, and this 2 is basically now your address sent as a writing back into the memory. So that's what happens in the registered like address calculation of the memory at the EXE phase in a very detailed sense. So Kevin, you are trying to point out to this one, right?
Yeah.
So for everyone, yeah, so I was trying to make it like, keep it simple for time being, since it is the initial set of classes. But since we have that, that question raised, so this is the real picture of how the assembly level code of store word R3, R5, R2, which is kind of equivalent to this one, this top level writing of the assembly equivalent. This is what the real assembly program will contain for you. So if you recall your assembly language skill, okay, and in that case, yes, we have these 2 register fetch, R3 and R5 together at the instruction decode register fetch. Then R5 content will be used in the EXE phase to compute the address with combining them with these indices, immediate field, and then this address will be used to store things in the memory at the memory phase.
Hey,
Any other questions? Yes.
Somebody mentioned that this is called like the processor pipeline or something like that, and that you guys went over it in your CS47. I want to review this over the weekend. So is that like the term I should search for in your YouTube maybe?
Processor pipeline?
Or some, like how would I search for where you guys went over the cycle that you've drawn out here, like that the 5 different steps? Because apparently that's something that you guys went over in 47. This is just review?
No, this 5 cycle is like in 47, we kind of mentioned it very quickly. You
Okay.
can watch out my today's class in the YouTube channel. Also, like it's the same, basically same piece of example I explained in terms of 47, little bit simpler. But we will deal with in detail with this cycle in this semester. Like this is our bread and butter in this
Okay.
course. Okay, so we'll keep on coming back to this 5 cycle. I'm just trying to put the stepping stone there. Okay. So, okay, good discussion. Good discussion. So, any other question?
I have a question about the ALU.
Yes.
If, for example, instead of 10 and 20, we did like 65,001, like the max integer, like +1, and we cause an overflow, how would the controller know like the ALU had like an overflow?
So ALU has an overflow flag. What I am showing here, very simplistic model of the ALU, which has nothing but OP1, OP, 2 operands, 1 operation, and the result output. But ALU will start having more and more things on top of that. One of them is this overflow flag, where it basically sends back the signal to the controller that, hey, this result is overflown. So do some action on top of that.
Okay.
Okay, so does that answer your question, Evren?
Yeah.
Okay. Did I say your name correctly? Evren, right? Evren, or how do you say your name?
Everyone, yeah.
Evren? Okay, okay. Thank you. What else? Anything else? Okay, so I would like to, okay, let's take 3-4 minutes on top of this just to put a perspective of the clock system on top of this before we go for a 5-minute break. Or, what's the time? Oh, 8:14 already 45. Okay, let's go for a 5-minute break now. Okay, we'll back about 8:20 and we'll talk about the clock system, little bit on the clock system. Okay, it's 8:20. Let's resume back. So far, where were we? Okay, so we wanted to do some study on the clock system and explain the concept to you. What is a clock system and what is the need? This is kind of an putting a base to that concept. We'll start with that concept today. So you see, there are several subsystems in a computing system, right? One is memory, which is on the motherboard. And on the motherboard, you see a processor, but this processor has subsystems like a controller, register file, ALU, and each one of them has specific role, what they do, right? In order to execute a certain program, like this one we just had an example. And not necessarily each of these component runs at the same speed or complete their given task in a same amount of time. For example, memory is a slower device than the register file and so on and so forth. So given a data reading task to the register file is faster compared to the memory, right? For example. So question become how to synchronize their operations. Like you saw that this is a 5-cycle operation, and there is an understanding between these components. For example, controller and memory. When controller sends out some read request to the memory, it kind of know upfront when to expect the data back from the memory. But how they synchronizes. The problem is something like this, right? So let's say you are in a midterm exam, and I give you the paper on a midterm exam, and we basically know that you need to finish it within 1 hour 15 minutes, right? So my expectation is that when I give out the paper, after 1 hour 15 minutes, you return back, you complete your task, return back the paper to me, right? But how do I know that 1 hour 15 minutes is gone? Simple solution is the clock. Simple answer is the clock, right? So we human goes with a clock, right? So let's say you start at 6. You start at 6, and then I know I am expecting the paper back at 7:15. So somebody is like kind of marking the time, and we know as long as this tick goes to the 7 and this hand goes to the 15, then it basically becomes this is 0. Okay, then basically it's a time that I expect the work back from me. So same thing needs to be done to synchronize operation between these components, this controller, memories, and all this stuff, right? So that specific system is the clock system. Clock system. And this produce a signal. This system produces a signal like continuous stream of logic 0 and 1. So let's say if we just draw them, like this is a train of pulses. So this is at logic 0, this is at logic 1, this is 0, this is 1, this is 0, this is 1. So that's one characteristics. And other characteristics is this: its edge are separated apart exactly as the same amount. So let's say T amount of time. They are all same, T amount of time. So they are all same. So basically, then the whole system, okay, these signals is connected to the memory,
Memory has a clock port. Same signal goes to the controller. Same signal goes to the register file, and same signal may go to the ALU. So they provide the timing sense to the whole system. And what is the agreement now between these different components? It is not in terms of hours, minutes, second, but in terms of how many clock ticks. Like let's say controller providing read operation, that instruction read or something at T1, this time point, and it expects, for example, memory to be completed within 2 clock tick. Means at this T3 point, it knows memory will return back the result. So in a sense, it is upfront specified between the system that which component takes how much time. So in this class, we'll simplify our viewpoint that assuming that most of the time, most of the time we'll assume they basically takes one single clock cycle, and we basically bound our discussion mainly based on that, unless otherwise specified. Okay, but in reality, they basically operates in different pace, and they need to be synchronized, and that's where the clock signal is important. So bottom line is this: clock signal provides a time reference. Clock signal provides a time reference to all these components, and each component has a pre-arranged agreement that how much clock tick they will consume to complete a given task. Question?
Is a clock tick equivalent to one time period?
Yes, clock tick equivalent to one time period in general sense. All the computing system, we can assume for our discussion purpose, they look for this transition from logic 0 to logic 1. So this is one clock tick, this is another clock tick, this is another clock tick. Usually nothing interesting happens during the falling part, like when logic goes from 1 to 0. But again, please note down, I said very loose term that nothing happens during this time, but down the line, 4 or 5 lecture down the line, when we start discussing about the sequential elements, storage element, we'll see this down part has its own significance. But for time being, just assume that main operation things happens at the rising clock edge of the system.
Thank you.
Okay. Question?
I also heard something about, I also read in like the first lecture about the processor that we're going to be making. The memory is going to be word accessible. I remember that last semester, it was supposed to be memory from the CPU's perspective, memory was byte accessible, and now it's word accessible. So how's it different this time?
Right. So that's a good question. So I'm actually now sharing these questions with you guys. So Kevin, so it is not mentioned here. Okay. Anyway, so the question I get from you is that in the CS147, when you studied the assembly language and processor programming, we talked about the memory having a byte addressability, and then we talked about something about like reading 4 bytes at a time for instruction fetch and etc. So in this class, we assume, unless otherwise specified, that memory is word addressable. Why? Because we want to simplify the memory model to be implemented at the project. So we don't want to have the complexity of having a byte addressability in our processor implementation. Probably you remember all the complexity arise due to the alignment issues.
like you cannot access word from a address which is not divisible by 4, that word alignment, by half word alignment, all these issues. We don't want to face it in this class because that doesn't actually make sense to understand the computer architecture itself. This is somewhat imposed problem from device level, and also like how granular we want to go from the data access perspective. Means that can our system at high level support like a byte size data? For example, character is a byte size data, right? Can we go into that granular level? Since in our class we'll be mainly dealing with the very simulative environment, we don't need to go into that granularity. So we confined ourselves in the word addressability to make our life simple.
Thank you.
Okay.
Professor.
All right. Yes.
It's Akash. So I had a question about a clarifying question about the register file. So you said in memory you can't do read then write, right? And then, but for a register file you could do read, you could do write after read, right? You could do that.
Yes. You are talking about the back-to-back read and write, right?
Yeah, that's
So
because
for the register file, since it has separate what is that, data out, separate data out port and separate data in port in a conception, so we can do a back-to-back read and write. But for the memory, since it has only one bidirectional port for either data can go into the memory or data can come out of the memory, that's where we had that restriction of back-to-back read-write operation, that you cannot have it immediately after read operation, because once the read operation is done, data will come out through this line, and at the same time you cannot send another data in. They will conflict in midair, basically, right? Data. So that's why we cannot do it at that point.
okay, thank you.
Okay. So Akash, may I request you to have at least your profile picture on the Zoom, so that at
Oh yeah,
least.
I actually had my video on. I could turn it back on. I just turned it off for the break, then I forgot.
Okay. Okay. Thank you very much, Akash. So I just want to, yeah, video is fine. Like you can turn off your video, but if you have the profile picture on, then it will at least I can see your face.
All
So video is not a must, but if you guys can please make your profile picture off for the Zoom, set up the profile picture. Okay. What else? So Catherine, probably I will come back to your question in next class, okay? We don't have that much time. Let me see if I can answer the other question. Could you please explain the high-Z state as described in slide 8 and 9? Okay, high-Z state, it's something like this. Let's see. So let's say in terms of electric circuit, okay? In terms of electric circuit, let's say, okay, a very simple one. So I have an electrical switch connected to a battery and connected to a light bulb. Okay. Now at this point,
we can't see the Jamboard, Professor.
was that? Oh, sorry. Thank you very much. I am not sharing this. Okay. Actually, I need to share my Jamboard. Yeah. Yeah. Thank you very much. Yeah. So I hope now you guys see it. So we have the switch. We have a battery connected. We have a light bulb. And the switch is open, right? So nothing is glowing up in the bulb, but it is still connected to the battery. It's still connected to the battery, somewhat connected to the circuit. So this is what is the zero state.
Okay. Now let's say you make this switch closed. Make it closed, right? Closed circuit. So what happened? This bulb will glow. This is what is the high state or logic 1 state, conceptually. Now, let's say you are in a destructive mood. You basically take out everything out of this circuit, take out the bulb out of the circuit. What happens? You will say, okay, this is not glowing, and this is a zero state. I would say no. What does this mean is that it is not even part of the electrical circuit anymore. You just destroyed everything. So that's an high state. So electrically disassociated, disconnected from anything. That's called high Z. Is that clear, Christina? Makes sense?
Yeah, that makes sense. Thank you.
Okay. All right. Now from the Alexander, let's see. So Alexander asked this thing. 147 DV instruction set to define push and pop operation like this. Okay. Okay. So push operation stores a value on top of stack and decrements stack pointer by 1. Pop. Okay. So since each memory address is identifies only 1 byte, shouldn't 8 memory address space, etc., etc. Okay, Alexander. So as I mentioned, also the Kevin's question, right? In this course, we will assume a byte addressable memory. In fact, if you look at that instruction set architecture that we started with, we defined at the lecture 1. It says in the memory section, it is byte address. Sorry, it is a word addressable memory. That means each address contains a word. Okay, so that's why it is stack pointer moving by 1 is sufficient. It's a 1 address space. But in reality, you are right. Like I'm not sure about the 8. 8 is like a double word push, but 4 is sufficient because a 1 word is a 4 byte. So you need to move the stack pointer by 4 address, 4 amount. But if you want to make space for double word, then you need to move the stack pointer by 8. So in reality, yeah, that's right. But in this course, since we are assuming our memory to be word addressable, that's why the processor you will be implementing will need to move the stack pointer by 1 address. Make sense, Alexander?
Yeah, thank you.
Oh, okay. So you had an amendment. You need to have a 4, not 8. I thought you can edit the discussion topics, no?
It said the editing was disabled, so I just left another comment.
Oh, okay. Let me see. Okay, can you send me an email so that I remember and kind of, I probably didn't mean to do that.
I see, sure, yeah.
Okay, sure, thank you. Okay. So, since I'm sharing the this page, okay. Now we are left with the Catherine's part. Let's discuss it next day. Okay, it's a little bit longer. We'll do next lecture. Okay, Catherine, is that okay?
Yeah, it's fine.
Okay, now let me spend a little bit on the logistic part. So hope you all know about the homepage. You visit frequently, and you will notice there is an announcement section. And what I'm planning each Wednesday after the class to post an announcement which will contain the next week upcoming task and what lecture you need to review and so on and so forth. For example, last week I had this announcement up. I hope all of you guys have noticed. So basically it contains what are the lecture topics you need to review for the next week before coming to the class. And also it has the activity list for it. What needs to be done or you should do during this time, this week.
So watch out today also, like after the class, watch out for today's announcement, which will go for the next week, which will basically give you some guidance for the next week activity and task for you. All right. So with that 8:40, we have 5 more minutes. 5 more minutes. I wanted to do some group activity, but not really. Okay. Did we do that class poll of this thing, your activity? Did you do any class polling today?
No.
No?
Nope.
Okay, let's do that. We have some minutes. Is just this preparedness. Let me see who. So you can take it anonymously. Let's take a minute to do it.
Hey, Professor Rob, when is doing the poll, I just had a quick question.
Yes.
Are you gonna go over the assignment 1 and what's expected in class and everything, or do you just want us to like read it and do it on our own?
Project 1, you mean?
Yes.
No, actually, you need to go to the project 1. I'll show you. Where is the assignments? Project 1, and each of this project has an introduction video, what you need to do. It has some guideline, so you need to watch them out. And if you have questions, then come back to me.
All right, sounds good.
Okay.
Thank you.
So please, but I think for the project 2 also has a similar setup, I believe. Let me just quickly check. Project 2, yeah, it has some introduction, some of the guideline you need to watch out. And for project 3, I think at least I have the introduction. And in fact, for the project 3, you will find out in this introduction video that each of the lab from that time onward is a guideline and task for you. So I didn't have any guide for this project, but please go through the project assignments and make sure you watch these videos and understand. And if you have questions, then come back to me. All right, we have 2 minutes, and I think polls are kind of done and polling. Let me share the result. So I see the first question was, watch the lecture video for today's topic. 55% said all of them. That's good. For rest of the 40%, please do not fall behind the class. Even if our discussion is mostly to clear up the concept, and I see that some of the concept I need to like explain to you apart from the videos. So that's what we are doing in the class, and from like maybe next or tomorrow, it will be more like, again, you drive the class with your questions. Okay, so you need to watch the videos up front. Lecture videos are all there. What you need to do are all in the announcement. Please do it. Similar goes with the reading the lecture notes. 63% said yes, that's good. For the rest of you, please do it. Note question notation, 10% yes, noted the question, I saw it. Note of 64%. Don't have any question, 26%. So again, please, if you go through the videos and lecture notes very minutely, I believe you will have questions. You will have queries. So please be sure you go through them very particularly meticulously, and start adding your question. Ask a lot of questions. Otherwise, just be sure you're not understanding the whole subject if you don't have question. Okay, that's the basic bottom line here. All right, so we are end of here now for today's class, and we'll see you on Monday. If you have any questions, just send me over email. Okay. Stop share. Okay, good night then, and let me just